Are we sure? Oh yeah, there we go. Okay. If you still can't hear in the Zoom, let me know. Hopefully you can now. Okay. So where were we? Sorry about that. So tokenization, like I said, is one of the first steps in pre-processing, and it's how we split down a raw text document into something that's more comprehensible, typically words, but you might also do it at something at a higher level of granularity, like splitting on sentences, for example, is another natural one, or splitting on paragraphs. And you could also tokenize even finer than words, but typically words is the level to which you would go. So now that we have tokens, we can do a variety of things with them. One of the first things that you want to do is group them together into more units of meaning. So one important technique here is called W shingling, and a W shingling is a subset of unique W unique contiguous tokens. Basically, you look for unique subsequences of a particular length in the tokens, and you put those into a set. This is useful because then if you find all these unique subsequences, you can compare these to the subsequences in other documents, and that suggests something about their similarity, right? So that sounds a little esoteric. If you look at the "this is a test, is a test, is a test" sentence there, it becomes more clear what it is. So if you start with the window, let's say this is a trigram shingling, right? So if you start with the window at this, then you take the first three tokens there, become a subsequence, right? That's obviously unique because it's our first one. So this is A. Then you go starting at is, then you have is a test, and then go to A, that's a test is, and then you get to the test, and then you have test is A. Now, when you go to the is again, the second is in the sentence, that trigram there is not unique anymore because we already have it in our set. So you continue like this, the string, and then at the end, you get this set of 4 tuples there, 4 trigrams, right? So that's what this is talking about. We can use these also not only at the word level, but we could use these with characters. So if you look at the word lasagna, you can do the same thing. Really, you could do this with any sequence. It's just that it has particular applications for us here. One of the special things about this is that when we have these n-grams, this n-gram model is what's called a Markov process. If you've taken some of the higher math classes, you might have heard this term before. If not, don't worry at all. Markov processes are special kinds of statistical / mathematical processes where the next event is only, the probability of the next event only depends on the current event. And this is really useful because then we can do all kinds of computational modeling that's much less complex than it would otherwise have to be. So it's a very valuable thing. Another step that you want to do in pre-processing is what's called lemmatization. And this is how we get words that all may have different, conjugations, for example, or maybe an adjective or adverb form to something that is standardized. So what you do is you remove the morphological endings of words and keep only the base or the root. In this case, in natural language processing, we call that base the lemma, hence lemmatization, right? So a great example is right here. So if you look on the right-hand side of that figure, you can see change, changing, changes, changed, and changer. The lemma here is change, right? That's the fundamental unit of meaning, and they're all referring to that same concept. And the concept is actually called a lexeme. So change is the lemma, and this is different from stemming, which is, I guess, a more simplistic technique, you might say, but it's just a different technique where you would take the longest subsequence that begins the first character. So if you look at change on the left-hand side, or you look at the left-hand side of the figure and you see change, changing, changes, etc., the way you would get CHANG there as their stem, right, is you would start at the first subsequence and then you continue until you have a difference, right, between all the subsequences. But that's less useful because CHANG is not a unit of meaning in the English language. That's basically what lemmatization is, but the real reason this is valuable is because now all the words can be standardized to a particular form, and we don't have to deal with all these different conjugations or maybe different parts of speech that capture the same fundamental meaning, right? Another step, so tokenization and lemmatization both are basically taking this raw text and making it more rich and having more structure, which is easier to work with. So another technique for doing this kind of task is part of speech tagging. This is pretty intuitive. It's exactly what it sounds like. So if you have words in a text, they all have parts of speech. The most basic would be just like nouns, verbs, adjectives, adverbs, etc. So what you do is you go through the text and you mark each non-article, because articles can basically be ignored. You mark each non-article with its part of speech, right? And you can also make this more granular, and that makes it more useful, where you can say this is a proper noun, or maybe this is a person, this is a location, and then you can derive more information from the text and maybe figure out, like, if it's biography and you figure out the person who's occurring the most, perhaps that's the topic of the biography, for example, right? So those are some of the pre-processing steps. And now we're going to move into more of techniques and things you might want to do in natural language processing. So one of these is sentiment analysis. And this is a problem within natural language processing, something that you may be trying to do on a particular text or a particular data set. So sentiment analysis tries to find the sentiment of a text, right? What this typically means, you could feel like it's the emotion, but it's actually more subtle than that. So one is polarity, which is the orientation of the emotion, whether it's positive, negative, or neutral. You could think of this as like -1 or -1, 0, or 1, right? So you want to find the direction of the text in how the writer is writing. Do they feel like whatever they're talking about is good or bad, right? And there's also subjectivity. If you're taking composition classes at UF, as most of us have to, you'll be familiar with this. This is how feeling-based is a piece of text, right? Versus how much does it depend on the logic. And so you'd use techniques to analyze like the presence of emotive words and their frequency. And then you might be able to decide that is more subjective. That's of course, very hand wavy, and what you actually do is more complex. This is sentiment analysis similar to the task of emotion detection or maybe emotion classification. So you'd say is something happy, is something sad, is something angry, something jealous maybe would be another more subtle one. And this is similar to, but distinct from polarity, right? Because sad and angry are both negative, but they're distinct in like what kind of negative they are. Basically, they're in some kind of higher dimensional space. So what this would look like then is if you look at this sentence here, so you can see we have two clauses, right? And one of the first things we could do is part of speech tag, and we'd find that pizza is a noun in the first clause, right? And it's followed by a verb. And so it's the subject of that clause. And so then after the subject, you find this adjective good, and we know that that's a particular attribute then of pizza based on the structure of the sentence. And then we can say that has a positive sentiment about the pizza, right? So the person is making a positive statement about the topic of that. And then the reverse would happen in the second clause where it says the service, that's the subject, which you can figure out with part of speech tagging and some analysis of the structure. And then you have was slow. Slow is typically negative, not always. And so then you find the sentiment that's negative. We did not mess that figure up. Just want to say that we just sourced it and we had to change it. But that's what it might look like, right? Jasmine?
Sure. So I don't know. So from this point on, we're going to go into some more advanced, just a little bit more advanced, and a little bit into the machine learning aspects. So NLP. So NLP itself is actually considered a smaller subset under the umbrella of machine learning, but it's just machine learning applied to different tasks related to natural language text and spoken as well, and speech as well. So one major field within NLP is topic extraction, which this sounds exactly what it sounds like. You're trying to find the major topics and main points of, say, a Wikipedia article or some newspaper, and maybe you want to do it by paragraph. So there's actually two different levels of granularity. When you're talking about topic extraction, you're finding high-level main ideas that do not necessarily have to be exact words within the passage itself. You do not have to, say, find a word that exactly matches the topic of the paragraph. However, when you're doing a finer granularity like keyword extraction, you're actually looking for important words that already exist within the text. So you're scanning the text itself and trying to rank and rate the words with some weighting system. So there's actually a diverse array of different ways you can represent and organize text. So one of the most popular methods is word2vec, which gives a lot of context. It's trained through essentially a neural network where you're passing sentences through it, and then the trained weights essentially form vectors. So it's a fixed length vector, which means it does not matter what word you're trying to represent, it always outputs a vector of the same length, let's say like d-dimensional. So it'll be a vector of d numbers. And so you're essentially casting these words into a numerical high dimensional space by converting them into vectors. And one quirky feature about word2vec is that there's an additive property where approximately you can sum the semantics or sum the meaning of these two words, and you will get a new vector that is at least very close to, if not exactly equal to, the vector representation of summing the meanings of these two words. So for example, let's say that V is a function that just outputs the vector representation of a natural language word. So king plus female, naturally to us, to humans, would logically be queen. But if you were to represent that numerically with vectors, you would get a similar vector by summing the two vectors for king and female. And also something as just a set of all unique words within like a corpus is called a vocabulary. But usually in pre-processing and systems where you're dealing with NLP tasks, you usually want to do some stemming so that there's different endings to the same word. You don't want to repeat the same word with different endings. That's just a waste of memory. So usually you would do some sort of stemming first before you finalize the vocabulary. And a corpus is just a set of documents that you're working with. So it's just like a data set where each individual piece of information is a piece of text. And with that, we can go into, I guess, a more advanced way of organizing the vocabulary by finding the frequencies of them or the counts of the unique words in each document. So this is what's called a document term matrix, which is the giant rectangular matrix with the rows being aligned with individual documents, so the individual text you're working with. And then the column space is just has the same size or dimension as the vocabulary. So each column will be aligned with the specific vocabulary word from that corpus you're working with. And so the entry at the ith row and jth column would simply be the frequency, or basically the number of times of occurrence of that particular word, of the jth word within the ith document. And finally, there's a knowledge graph, which is pretty advanced above everything before that. So a knowledge graph is just a huge network representation of entities with relationships represented by links or edges. So essentially, you can think of it like a social network, like Facebook or LinkedIn, except that the nodes here represent ideas that are real words or that are real items inside the vocabulary. And you can see an example on the right, which is about the Disney company and some of their productions, and obviously relationships, including some hierarchical relationships between different productions. So as I said earlier, that NLP is kind of a subset of machine learning. Oh, it's not just a subset, but it's actually, it just overlaps with machine learning, but NLP is so big in its array of different tasks that you can like apply deep learning as well to it. And it's just a general subset of AI applied towards natural language. So now, after that, let's head into like some basics of machine learning, just a conceptual overview of how machine learning comes into NLP. So one of the most popular models in machine learning that can work on words and work on phrases and sentences and so forth is LSTM, and it's a variant of bidirectional or bi-LSTM. So essentially, this is just a elongated recurring neural network that can take in a string of words. So each word would obviously have to be converted into a vector form, into a fixed length vector, in order to be fed into a neural network. But essentially, this long neural network can be trained to accomplish a variety of tasks, depending how the exact architecture goes. So you can use it for sentiment analysis, document classification, making a summary of a large text, or actually generating new text based on previous text, using previous text as like context and hint. So deep learning, as you saw in an earlier picture, deep learning is a subset within machine learning that focuses on using like very deep neural networks, meaning they have many parameters and typically a lot of layers as well. So essentially it's like a black box of you don't really know what's going on, but after a lot of training, you're able to accomplish some very interesting, intelligent tasks. And that can be applied to NLP without problem. So BERT is one of the revolutionary or one of the major turning points in deep learning as it applies to NLP. So it is published in 2018 by a group from Google, and it stands for bidirectional encoder representations transformers. So don't worry about the terminology, but you can think of it as a very like advanced, very advanced neural network that has like many layers trained. In fact, it has like 110 million parameters across these layers. So it can take in a maximum of 512 tokens in a sequence. This is just a fancy way or technical way of saying it can take in a sequence of 512 words at a time, essentially. Could be a phrase, could be a sentence, it doesn't care, as long as it doesn't overreach this 512 word limit. It can take them in simultaneously. And this is one of the benefits of BERT, is that all tokens can be considered simultaneously and weights can be updated together, as opposed to LSTM earlier, which you have to train from like left to right. You have to wait until for the ith word to be processed, you have to wait for the I-1 word to be processed first. So BERT has this advantage of considering the context across the entire phrase simultaneously. And there's other deep learning neural networks as well, such as the convolutionary neural network, which uses like a window or a filter of weights to scan through the text. So this is actually a picture from the actual publication of the BERT model. You can see that you can divide up or tokenize a sequence or a phrase. Here it is like, my mask is cute, and the separator, he mask play ing. So this might seem strange at first, but the mask token is just trying to cover up the word and hide it so it can train and make the neural network try to guess what the word is from the surrounding context. And there's 3 different types of tokens that are combined together. So for each word or for each token, there's the embedding itself, which is just the numerical vector representation. Then there's a sentence embedding. Is it from the first sentence or a second sentence? So sentence A or sentence B. And then there's positional embedding, which is telling just like an array index, it tells the position of where each token falls from the beginning. And this is a convolutionary neural network, which is shortened to CNN. And as I said before, it uses one or more filters. A filter is just a smaller matrix that you can act like a scanning window that just moves or shifts across the text one at a time. And so you would have new matrices that are essentially the element-wise products of these filters and the word embeddings. And with all the machine learning, like theoretical stuff out of the way, I'm going to go ahead and introduce some major high-level Python libraries that you can use if you're interested in developing NLP systems or just playing around with NLP for the first time. So as far as beginner-friendly ones goes, I was just suggest NLTK, which is a natural language toolkit. That's what the acronym stands for. But Spacey is also pretty high level, and there's a lot of rich documentation that you can find online. It's easy to follow along. And of course, there's other ones like Standa and algorithms which approach NLP from their own aspects. And finally, there's Beautiful Soup, which is not actually dealing with any models used for NLP, but rather it's just a handy tool in the earlier stages of gathering text from the internet, which is called web scraping. So you can enter like a URL with certain functions from Beautiful Soup, and you could actually scrape the text off the websites aligned with these URLs you entered. And with that, let's do like a quick demo. This is actually a link to a Google Colab. So I would suggest that you use a laptop rather than your phone, but okay. Yes. All right. I believe you have to be logged into Google. Yeah. So everyone like having any trouble or? Oh yeah. Sorry. Actually, let me also put this in the chat for. So yeah, I didn't get it. Just a random article. So I'm assuming everyone like is not having any more trouble. You just need to log in with a Google account. You don't need to install any software. This is all online. This is all hosted online by Google. So. Okay, so let's start running this. So I'm going to start up with NLTK. It's just downloading some necessary tools under spelled. Oh, saving failed. Okay. And then tokenization is an easy task. So you can see it immediately giving a check mark here. It doesn't use much computation at all because it's simply splitting by space. So you just have the individual words. This is just a very long list of the words. And sentiment analysis, you can use with Alexa, and then you import something called a sentiment intensity analyzer from NLTK.sentiment. This is a tool under NLTK that tries to provide functions for different metrics, such as Polarity Score. So copy process is the variable that's assigned to the text you saw earlier. And we're going to look at the polarity scores. So as you can see, it prints out a negative, neutral, and positive. And these would sum to 1 together, but this is just like a distribution of the polarity. I guess it kind of makes a little bit of sense because if you just look at the negative and the positive, the negative outweighs the positive by a bit, obviously by the introduction of vulgar words throughout the text.
Am I reading this right?
Yeah, I mean, most of the words do not carry any emotional intensity. I believe top, like articles I and trained in am. See, these are like, these do not have much meaning, do not have much emotion with them. So that's just the majority of words. So if you actually throw out the meaningless words, or rather the neutral words, and then do it, then the negatives would obviously outweigh the positives. So with this cell, actually, did it run or not? Hit install. So this is a different Python library aimed to scrape online newspapers and online like articles. Okay, so installing success. And then you just have to provide a URL to any article online. And this has its own built-in Polarity Score function. So now I want to introduce Spacey. So we're done with the MTK. So Spacey is another easy to use and high-level Python library for natural language processing. So with Spacey, though, you do have to download like a corpus. Just to speed it up, I downloaded a small version, but essentially, this is just a commonplace corpus for English text. And the SM at the end stands for small. So right now, this is downloading a small version. You can switch it to a large version, but it takes way longer to download and doesn't always work. So let's say I have two different pieces of text. So one specific task that Spacey can accomplish is try to find the document similarity. So it's essentially just a score from 0 to 1 that tries to say, hey, how closely related or how closely matching these two texts are. But before you do that, this line on top, you have to load the recently downloaded corpus and register it with Spacey. And then that basically forms the model. You can put any name for it, but I just set the model to the variable NLP. And with that, you just use the model directly to call upon each text, and that creates a document object here. And finally, at the end, the similarity function creates the or generates the score. So you can see that it is about 0.72 or 0.73 if you round, which makes sense because these are like two different ways with slightly different tones of saying the same thing. So they are pretty similar. And now with the last stage of the demo, I'm going to go directly to utilizing BERT. So utilizing this deep learning model to show you some cool tasks that only deep learning can accomplish against what you saw earlier. So let's install this. Okay. And just like Spacey before, Hugging Face is the libraries, Transformers library is actually from Hugging Face, and they declare models as well using their own methods. And whenever you use a model for the first time, in this case, it's BERT-based uncased. This is just like the default BERT without modifications or variations. But they have a lot of different variants of BERT that you can try, like the stale BERT, which is a lightweight version of BERT. You just have to specify the name, and if you're loading it for the first time, you would see the progress bar of download. So now the cool part about Transformers, about this deep learning library for NLP, is that you can create pipelines aimed at different tasks. So what do I mean by tasks? Well, tasks are just specific actions of NLP that you can directly specify per pipeline, like question answering or summarizing, for example. So let's start the question answering pipeline. So again, you can provide your own model, like your customly instantiated model, like I did up here, but I didn't do that here. So if you don't provide the parameter for model and for a tokenizer, then it goes to default values. And the default for this one is distilled, or the lighter weight version of it. And again, because I'm using bird base case distilled or dash squad for the first time, it's downloading and showing the progress bars. And so say, let's ask a question, what is the meaning of life, the universe, and everything? So if you notice from the book, it's obviously 42, but for the pipeline, it doesn't know any of this. So you need to provide some context. And let's say you give a clue saying 42 is the ultimate answer. It would deduce from your clue that the answer to this question will be 42. And it also gives like certainty. So it's almost 70% certain that 42, given the context, would best answer the question stated previously. Yeah. And let's have a longer text. So this is actually also copied from one of Aesop's fables. It's a famous one, the tortoise and the hare. And let's declare the pipeline. And this one, the default model used by the Tokenization pipeline is this one right here. So it's like a different version to Spellboard, but let it load for a while. So essentially, after it's ready, regardless of what task you're doing, you just have to call the pipeline directly, like pipe, and then in parentheses, the text you want to process. And after summarizing, it actually returns a list. So you can actually summarize many texts. If I had like a list of individual strings, it would return a list of dictionaries. But since I only have like a single string here, it's essentially giving me a list with a single item. I get that item, which is a dictionary, and then I get the summary text from the key here. And you can see it's a shortened version of the story, which may not make sense because this is a relatively short snippet of text. And by default, the summarization performed here is extractive, meaning it doesn't summarize with new words or doesn't reword the original text. Instead, it just chooses the most important sentences while trying to discard what it considers insignificant sentences. So it's just shortening this or truncating.
I have a question.
Sure.
So it took sort of the story of like the error and it created a summary out of it. So if you ran that summary through this again and asked it to summarize that, would you get an even shorter summary?
Probably, or I would guess maybe one sentence shorter, but if you would have a single sentence or just a really short phrase, I don't think it usually stays the same, essentially. It doesn't do anything.
Okay, so
This is reaching that point.
Like
Yeah. Right. So, and then another example would be text classification. So they actually give it a really misleading name. You might be thinking text classification is trying to obviously label a piece of text into a specific class. Like if you know anything about machine learning and classification, you want to actually label the correct class for a piece of text. But this is just sentiment analysis all over again. They just call it text classification because they're classifying like, is it positive, neutral, or negative? So the classes themselves are like one of the three polarities. So this is just Hugging Face's own way of implementing sentiment analysis. And finally, this is probably the coolest feature, which is text generation. So the AI here will eventually try to come up with text that logically and fluently follow the text you provide as a starting point. So say I flunked out of school, that's like the starting point text. And let's see what the NLP system will generate. Okay, so the next day was the one I'm just studying. And it stopped right here. So I guess it took the negative sentiment into high consideration and saying the next day was very horrible, obviously, for the whoever was saying I flunked out of school. And it's using the context of school to say, okay, I was probably studying at some university and so on. So it's basically using contextual clues from your starting phrase that you provided here, essentially. And this is using, you might have noticed, this is using GPT-2. Everyone heard of like OpenAI and like how they have like GPT-3 right now? Which is just a really, this is a really huge modern model that kind of like learns its knowledge from the entire internet. But GPT-2 is like older than GPT-3, so it's just not as large and well built. But it's like a generalization AI. Yeah.
I'm noticing that this generated text is not the same as what I have here. So is it like introducing randomness into like?
Yeah, there is a. Yeah, actually, I can read on this. So I actually played with the GPT-3 version, like their playground for text generation. And okay, look, see, it's different this time. So with the GPT dash whatever number with these AI models, there's something called like a temperature, which alters the probability. It's like almost like a measure of how strict you want the model to be. So, but they just have a parameter called temperature. I'm not too sure of how to implement in code, but if you go to like GPT-3's website or go to the playground, there's the bar you can switch across to change how like flexible or inflexible the probabilities are of changing content. Yeah. And that is essentially a demo. Anyone else have any questions? Yeah, I think we're good. Yeah. Yeah, thanks for sticking with us. Yeah, I'm gonna stop the sharing. Okay, stop the recording.